weird. Okay, so welcome to our first physical science virtual session of semester 2. We're gonna go ahead and get started here. I'm gonna share my screen. I did wanna add one little detail in here, but I think I could do it just by showing the biology slide. So, we'll have that open too. Okay, so welcome everyone. Come on, Word, why are you opening everything? Okay, we're gonna get started here by talking about some course expectations. Just because we have a lot of new people to the course, and it's also helpful just to be reminded of what's expected, what you need to do. So first things first, we're gonna review the course expectations. Then we're going to review how to find the number of protons, neutrons, and electrons using the periodic table. And then we're going to talk about charged atoms and valence electrons. So 3 topics that are related but are going to feel pretty different here, really gearing us up to learn more about reactions and how atoms actually interact with each other. So expectations for the course, right? Make sure that you're attending all the virtual sessions, like right now. If you can't attend it live because you have a job or you have a different class at this time or you have something else going on, just let me know, right? Every session's recorded. You can always go back and watch it after. You could also rewatch it, especially if the content is something that you need to review. We are going to do 2 in-person or virtual labs that must be turned in by the end of the semester. Those will also be recorded. So you can attend them in person, you can attend virtually. Or I may give an option for how to do the lab at home if virtually doesn't make sense, because sometimes it doesn't. Read the lessons. Some of you guys may have already noticed that in this particular part of the course, there's some lessons that don't have assignments. That material is still going to be tested. I'm going to show you what I'm talking about in Canvas in a moment. But that material is still going to be tested, therefore it's very important that you go through those lessons, even if they don't necessarily have an assignment. Take notes. Remember, you can use your notes on the exam, on the module tests, on the discussion-based assessments, on the assignments. So if you have notes, it's only going to help you. Also, ask me questions, right? It's so helpful when people email me, hey, the instructions for this assignment say this, and I am not sure what that means, right? Because sometimes I don't realize that they're not clear until someone points it out, and then I'm like, oh yeah, this is a little confusing, and I can change it or elaborate. All right, and then we're gonna look at Canvas really quickly here. So, did I close Canvas? That's weird. Always have Canvas tabs open. So I added a couple things to the course that I think are gonna help with the organization. So in Physical Science B, right, please make sure you're looking at the calendar. Our next event is gonna be a lab on February 28th. That's gonna be at noon. You can attend that virtually or you can attend that in person. All right, other thing that I added is modules. At the very bottom, if you scroll all the way through, there's a virtual sessions and labs section. This also tells you all the dates, right? So today, 2:13 virtual session, 2:28 lab, 3:14 optional work time. That means that I'm gonna be available for you at the school and you can come in and work or ask questions, but you don't have to, right? Another virtual session, a final virtual session, and a final lab. And then finally, another optional work time. So for example, today, once I have finished with this this presentation, haven't had enough coffee, obviously. Once I've finished with this presentation, it's going to be uploaded here. So the PowerPoint that we're going to be looking at will be uploaded here as well as the video. So if you ever miss any of the virtual sessions, they're all in one place. Okay. So back to science content. All right, I know you guys learned about the periodic table last year in 8th grade. If you're not in 9th grade, you've learned about it before. So depending on what school you were at, what teacher you had, you might have learned some of this stuff already. It might be a review, right? You might not have learned it at all. So I'm going to start with some basic stuff about the periodic table, right? Just generally about its organization. So it's organized by atomic number. So when we look at the periodic table, it goes 1, 2, 3, 4, 5, 6, 7, 8, etc. by atomic number. The columns, right, or up and down, are elements that are going to react similarly. They have similar properties, and we'll talk about why, actually. We'll explain why that is true at the end of this virtual session. And then rows, so going across, it increases by atomic weight. So the elements get heavier and heavier as you go across. There's some other general trends. We're not too concerned with learning about all of them. When you take chemistry, you're going to learn everything you ever wanted to know about the periodic table. So here's a picture of it, right? Looking beautiful, nice rainbow one here. In fact, I don't know where to put this little video thing so it's not in the way. We'll do it like that. Okay, so they even have the groups down here, right, of what these elements are organized into. And you'll notice that most of the groups are columns. So the alkali metals, these are really reactive metals, right? They're usually explosive. We have the alkaline earth metals, transition metals. I like this one, the basic metals, semi-metals, non-metals, halogens, noble gases, and then lanthanides and actinides, which honestly, they're this weird series of elements that you usually don't interact with necessarily. Noticing that we have the numbers here, the atomic numbers, and we have the names, right, and the atomic mass, which we'll go over. So we're going to play a little game. I'm going to post in the chat here a link to that rainbow periodic table, or you can use a different one if you already have one open. All right, so here's the rainbow periodic table. I just sent it to you guys in the chat. So open that up, because you need to be looking at one to participate in this game. And you're going to take a moment to answer these questions. And then we're going to go over them, and you guys can share in the chat, or you could speak. So let's take a minute to find the answers to these questions. All right, what you're doing is you're looking at a periodic table. Right above where you asked, I sent a link to one. You could also Google one, and you are answering these questions. Which element is heavier, boron or iodine? What is the atomic number of carbon, oxygen, hydrogen? Name 3 elements that react like neon, and name 2 elements that react like oxygen. just write it down on your computer or next to you, right? I'm not going to collect it or anything like that, just so that you're practicing where the periodic table is. All right, so we'll start going over them. David already gave us the first one here. David says iodine is heavier than boron, right? So all you really had to do here was find iodine and boron. So boron is here, okay? Iodine, way down here. So David is correct here. Iodine is much heavier, right? In fact, iodine's atomic mass is 126.9 and boron's is 10, right? So significantly heavier. All right, second one. What is the atomic number of carbon, oxygen, and hydrogen? So if you found the answer to that, go ahead and type that in the chat. All right, Elizabeth says carbon equals 6. Hydrogen is 1. Oxygen is 8. Excellent. Right, this might seem really simple. In fact, some people are probably like, of course everyone can find that. But I'm telling you, the more that you look at and use the periodic table, the easier it gets to find stuff on it. Because there will be times where you're looking for an element that's super obvious and you just can't find it because there's so many and you're just looking and looking and looking. So it's always good to practice finding stuff. Okay, name 3 elements that will react like neon. So for this one, you have to remember that elements in the same column will react similarly. So all we're really looking for here is 3 elements in the same column as neon. Zach told us argon, krypton, helium, right? Argon, xenon, radon, right? Excellent answers. So all these guys here on the far right, these are all noble gases. And they're called noble gases because they don't react with anything, right? So people, I think, named them noble gases as a joke, scientists, right? Because they're so noble. They're like kings. They don't do anything, right? Everything is done for them. So we will talk about why that's true, right? Because they all have something in common that prevents them from interacting. Oh, I see. Yeah, so Zach's exactly right. When you know where some of these are or you know something about them, finding them and answering these questions can be a lot easier. In fact, I play trivia. I'm obsessed with trivia. And every once in a while, there's a science question. Obviously, it's my category in geography. But the science question was, name 4 of the first 8 elements in the periodic table. And I got it right because I have them memorized creepily, which would never be useful except in trivia. All right, so if you ever play trivia, this could be useful. And then the last question, name 2 elements that will react like oxygen. So we already know where oxygen is. So naming two elements that react like oxygen, anything in this column you could put here. So sulfur, selenium, tellurium, or polonium. All right. So, and I like this. Some people writing out the name, some people putting the symbol. Both are totally acceptable ways. Sometimes the symbols can be hard, right? Because you might not know what it actually, that's the best name. I don't know. You have to look at some of these other names. Some of them are insane. Let's see, where's like some of these weird newer ones. Copernicum is named after Copernicus, right? A famous scientist. It just sounds weird. Francium sounds kind of weird. I don't know. There's some weird ones on here. Yeah, UUT. So this, it says unknown, right? That's actually, I don't know what year this periodic table is from. We would have to look up the most recent one. That element, as of the time this was made, had not been discovered. right? They might have discovered it at this point. I'm not sure. I don't really keep up with the discovery of the elements, but you see that a few times here. Like anytime it says unknown underneath the element where it should be an atomic mass, that means that we know that element exists, right, because of the periodic table, but we don't actually know what it is, and we haven't found it. Unpentrium, yeah. I'm sure it's hard to come up with cool names for stuff in the periodic table, but who knows? All right, so that was a good little review of like looking at the periodic table, where stuff's at. We're gonna review even further here, just what all these things are. So most of us already figured this out to some extent doing this activity, right? But obviously we have our name of our element. Our atomic number is usually located on the top. Sometimes it's in the corner, sometimes it's right above the symbol, right? It depends on which periodic table you look at. Our atomic mass is always a decimal number, right? Because the atomic mass is, we're actually going to round it for our purposes, but it is a decimal. And then I wrote here sometimes other stuff. Some periodic tables have a bunch of stuff on them. Some are super simplistic, right? This is the basics that we're going to need for this course. When you take a more advanced chemistry course, you'll learn things about shells, and you'll have S and P and Q and all this other stuff in there. All right, so this basically says the same exact thing. I kind of just put this in here for people who are going to be tuning in later and going through the PowerPoint. But it explains those things: atomic number, atomic mass, symbol, name. So important things about this is that the atomic number is always going to be equal to the number of protons and the number of electrons. So carbon has an atomic number of 6. That means carbon has 6 protons and 6 electrons. When it's a neutral atom, which carbon is pretty much always neutral. It's rare that you see a charged carbon atom. It happens, but it's super rare. Atomic mass is going to be our protons plus our neutrons. And sometimes people, okay, bye, Alina. Sometimes people are like, well, what about electrons, right? Do electrons have mass? They do, but it's so small. It's like 0.000000000000001 or something like that. I forgot how many zeros it is. I think it's like 23. So there's a lot of zeros there. It's a really tiny mass, so we usually neglect it. Hopefully you are recalling from middle school that protons are positive, neutrons are neutral, and electrons are negative, right? So if our protons and our electrons are equal, which happens in a neutral atom, then we don't have any charges. So we're going to look at an example when that's not true towards the end of this. Oh, and by the way, this is a Bohr model of carbon, right? It's a way to represent it. We just put the C in the middle so people know it's carbon. And then there are 1, 2, 3, 4, 5, 6 electrons floating around on the outside. We'll talk about those types of models later as well. Okay, so we kind of already did the first part of this, which carbon is a very interesting element here. All right, so we have 6 protons for carbon, which we know because there is an atomic number of 6. We also have 6 electrons for carbon because we know that it's a neutral atom, right? It doesn't say anything about a carbon-charged atom. And to find our neutrons, we're actually going to need to do our atomic mass minus our protons will give us our neutrons. Because if you recall, our atomic mass is our protons plus our neutrons. So we're just doing a little basic algebra there, rearranging. We always round the atomic mass, right? If it's 0.5 or higher, you round up. If it's 0.4 or lower, you round down. So we're going to round carbon's atomic mass down to 12. We subtract our number of protons, which is 6, and we get that carbon also has 6 neutrons. That's right, 6 protons, 6 neutrons, 6 electrons. Creepishly demonic numbers there for carbon, which is weird because carbon is the basis for all life. Crazy. All right. So carbon is one of the most important atoms because of what I just said. All living things are based off of carbon so far. There's some thoughts by certain groups of scientists that think, not necessarily like crazy scientists, that's not what I'm meaning to sound like here, but there are some scientists who believe that life in space might actually be based off of something not carbon, but similar to carbon. So for example, if we look back at our periodic table, there are lots of arguments and thoughts that life in space could be based off of silicon, right, or germanium, because they behave similarly to carbon. Pretty interesting stuff. Okay, so we did that for carbon. Now you guys are going to try to do the same exact thing for bismuth, which I happen to know is somebody's favorite element, Elizabeth, because it looks beautiful. But I picked it because it has a very different number of neutrons, right? It's not going to be 83, 83, 83. So take a second right now, calculate the number of protons, electrons, and neutrons for a bismuth atom. All right, seeing some people already having the answer here. If you were stuck, I kind of gave you some hints here. Electrons were 83, definitely. Protons also 83. And then our neutrons, we had to do a little bit of subtraction here. 209, right? We rounded this guy up because it's at 0.9. Minus 83, and that gives us 126. Welcome back, Eli. You might have to watch the video of the part that you just missed if it's confusing what we're talking about right now. Kendrick, what are you chewing on? Okay, so that wasn't too hard, right? In fact, you might have already done that in 8th grade, but probably needed a refresher. Now we'll talk about charged atoms. This is where it can get harder. And it's a little bit more realistic of real chemistry. So magnesium, right, is a metal. It's found inside your body. It's usually found as a charged molecule. We usually see it written something like this, magnesium 2+, meaning that it has a +2 charge attached to it. Now, the only thing that ever changes is the electrons. The neutrons can also change if you're getting into isotopes, but we're not going to talk about that right now. So why can't I get rid of the chat? What's going on here? Oh. Okay. So magnesium has a charge of 2+. Oops. Oh my gosh, what is going on? I can't get in my text box. Okay, I guess I just have to make a new text box. That's really weird. So if it has a charge of 2+, our protons are going to be the same exact number. So looking at our periodic table, we'll see a 12 for our atomic number. So magnesium still will have 12 protons. Now electrons. If we are getting an atom that has a charge of 2, a positive charge of 2, how many electrons are we going to have here? Keep in mind, in a neutral atom, we would have 12, right? We would have 12 positives and 12 negatives. They would cancel each other out. We want to be left with a positive charge of 2. So how many electrons are we going to need in this atom? Okay, I see a guess of 14. Now you guys are telling me actually the opposite. You're telling me we're going to add 2 negative charges, right? Electrons are negative. If we have negative 14 plus 12, we're still getting negative 2. So you want to think of it the other way, that we're going to have 10 electrons, right? 10 because we're going to have negative 10 plus 2, right? Which would give us 2. So keep that in mind. Think of it like subtraction. Put a negative sign in front of those electrons and think about how they're going to cancel each other out. So magnesium in the wild, right, which is basically in your body and in nature, is usually found in this charged state, which means that it's missing 2 electrons. I'll give anyone bonus points who can tell me why. Not right now necessarily, but this week, if you send me an email telling me why magnesium is usually found like this with only 10 electrons, there's a reason. If you can tell me why, I will give you 10 bonus points on your first test. Neutrons, we're going to do some subtraction here. So, of course, I covered up the atomic mass. 24. Okay. So, our atomic mass is 24.3, so we're going to round down. Our protons is 12. And so we are going to get 12 neutrons as well. It's strange the number of atoms that have equal protons, neutrons, and electrons. It's way more than you think it's going to be. All right, so just keeping that in mind, if you see that charge, that is telling you something about the electrons. It's telling you how many electrons there are. Okay, let's see. Now, all these text boxes. Did I give one for you guys to try? No. Okay, so why don't we have you guys try one? Let's see. Another common element is potassium, which is abbreviated with a K. I know, very strange. K is usually found as K plus. We'll do a 1 plus just so it's less confusing, with a positive charge of 1. So I want you guys to tell me the protons, the neutrons, the electrons for potassium with a charge of +1. So you may have to go back to looking. You may have to go back to looking at the periodic table, right, to see the numbers for this guy for potassium. Zach, you are on to something there with what you just said for the bonus points. You're 90% there. All right, so looking at the periodic table, yeah, Zach, if you have the answer to the magnesium thing, just send me an email. That way I can easily keep track of it, yeah. All right, seeing lots of different answers here. So if you looked up potassium on the periodic table, you should have seen an atomic number of 19. So that should give you the protons, right? 19 protons. For neutrons, we have to do atomic mass minus our protons. So we look at our atomic mass, it's 39.09. So we round down to 39. We subtract our 19 protons and we get 20 neutrons. Electrons, right? We're thinking about negatives and positives here. We want to be left with a positive charge of 1. We have 19 positive charges already. So in that case, we're basically missing 1 electron here. So we would have 18 electrons. Oh, good. Yeah. Okay. So this is just something to think about, right? That a lot of this basic stuff that we've possibly learned in the past about the periodic table, it gets a lot more complicated when we start looking at atoms interacting and how they appear in real life. So a lot of those metals that we saw here, notice I picked potassium. All of these metals here in this entire row, other than hydrogen because it's not a metal, lithium, sodium, potassium, all of these are usually found with a positive charge. Magnesium, all of magnesium's column. I always get row and column confused. Magnesium's column has a charge of +2 usually, right? Over here, we start getting charges that are negative once we get into the fluorines, the chlorines. So we will start talking about that more when we talk about reactions. Okay, oops, accidentally opened that periodic table again. So last thing here that we're going to talk about is something called valence electrons, which are a super important vocabulary word. I actually found this little vocabulary picture that I thought was pretty good. But valence electrons are the electrons on the outermost energy level. So the crazy thing about electrons is that they fill these energy levels. And the way that we draw them here in a Bohr model, they look 2D. But really, if you can imagine it, atoms are 3D, right? Electrons are moving around in a cloud on the outside. And even though they're in these energy shells, they are moving around a lot, right? So this is a very simplified drawing. Now, the interesting thing about this is that electrons also pair up, which we learned about a little bit last semester when we talked about magnetism, right? Electrons are spinning. They're like tops. They're spinning very quickly in one direction. And as soon as they have a pair, so they have another electron next to them, that actually helps to cancel out their spin, right? So it's basically like one spins to the right, one spins to the left. So they actually do pair up eventually when they're forced to. They don't like to pair up. They also have rules that they follow. It's very weird. The shells only hold certain numbers of electrons, right? It goes much further than the third shell. I'm just simplifying this quite a bit as we introduce it here. Oh, my dog. Okay, so there is a fourth, fifth, sixth shell, etc., right? And they hold different numbers of electrons as well. So the first shell of any atom only holds 2 electrons. So here we see sodium. The first shell is holding 2 electrons. The second shell can hold up to 8. Sodium has more than 10, right? So we see here 1, 2, 3, 4, 5, 6, 7, 8 electrons are filling up that second shell. And then the final shell for sodium, sodium has 1 valence electron. That's not good. There's a lot of emptiness there. That means that sodium is going to be highly reactive. Electrons and atoms want that outer shell full. That's why things bond. That's why they interact. Because sodium, for example, will bond with something like chlorine because chlorine has 7 valence electrons. And guess what? 7 plus 1 equals 8, right? So sodium and chlorine will basically form a bond together so that they can create full shells of electrons. So really, valence electrons are the electrons that are involved in reactions. They're the reason that reactions happen. Noble gases, their valence electrons are always 8. They're always full. They have a complete set of electrons, which is why they're not reactive. They don't need electrons. They don't care. They don't want to interact with anyone else. So we see 2 examples here. In fact, the way they drew this carbon is wrong, I have to say. In fact, we got to put an X on that thing because if I could get my annotation to show up. I'm going to draw you a carbon in a second. That's not how you draw carbon. I'll explain why in a second. All right. Nope. Okay. Regardless, carbon does have 4 valence electrons, right? It has 4 electrons. It wants 8. Again, carbon will bond with a lot of stuff, right? It's super reactive because it needs to fill that shell. Okay, so again, there's more shells. We're going to keep it pretty simple here. And when we start talking about bonding, we're going to keep it simple, but I will start going into some heavier chemistry stuff if it interests you. The scope of this course, you really don't have to know too much, right? But you should understand what valence electrons are. They're the electrons that fill up the outer shell, right? In the outermost energy level is technically the correct terminology. And they're the ones that are involved in reactions. So carbon, that's really weird. I wasn't even planning on like drawing the carbon because I knew they did it wrong, but now I'm glad that I did. All right, so we're gonna make little circles here. So if we look at carbon on the periodic table, right, which we have done multiple times, it has 6 protons, 6 electrons, and 6 neutrons, right? 6, 6, 6. So yes, Zach, you're 100% correct. That's exactly why carbon will react and bond with itself, right? And that's actually why carbon creates so many different compounds. Like diamond is made of carbon. So is graphite, the pencil lead that you use, right? All different bonds and formations of carbon. So when we think about these valence electrons for carbon, we know carbon has 6 electrons. So carbon is going to fill up its first shell with 2 electrons, right? Because the first shell can only hold 2 electrons. That's the rule. Don't ask me how these rules got invented either. I think I learned at one point how, but I can't even remember. It's just insane to me that electrons follow rules. All right, so the first shell will hold 2 electrons. The second shell can hold 8. Carbon has 4 more, right, to get to 6. Now, unlike what they showed, these electrons, which I apologize, my electrons are not the same size. They're a little bit special looking, but that's okay, they're there. The electrons will fill out the second shell like this. First, it's like when you're getting on a bus, right? If you're getting on a bus and there's a complete empty seat, you're gonna sit there before you're gonna sit next to somebody, right? Nothing irritates me more than when there's empty seats and creepy people sit next to me on the bus. I'm like, what is wrong with you? Sit in the empty seat, right? Electrons are the same way. They don't want to sit next to anyone unless they have to. So they will actually spread out in the second energy level like this, right? So that they're not next to each other. Now, if carbon had 2 more electrons, right? It doesn't, but we'll just say for drawing purposes, then the electrons would start to pair up because they have to. There's nowhere else for them to go, right? If you want to sit down, then you have to sit next to another electron. So that will happen, that they'll start pairing up. In fact, the first layer, I probably should draw them as a pair as well, but whatever. Semantics. All right, so that is how carbon looks in a Bohr model, right? Looking at these electrons, carbon has 4, it needs 4 more, right? We're gonna kind of leave it hanging there in this like vague area where you're like, all right, because next we're gonna talk about bonding in our next virtual session. And we're actually gonna see how these atoms interact and share those electrons. Okay, so, oh, I forgot I have to erase those. Quick question, go ahead. Are these required, the virtual sessions? Yes. And you will be happy to know that I have decided not to do exit tickets for them. But they are required. I am going to be writing down who's here at the end. So water molecules, right? This is where we start talking about molecules, bonding. We're not going to go into the specifics here, but this is a really good picture of a water molecule. And it's a little confusing looking, but you can see that oxygen has 1, 2, 3, 4, 5, 6 electrons here, 2 here, and then hydrogen has 2. Actually, this is a terrible example for me to show you because they share the electrons, so it's not going to be beautiful. But basically what's happening is oxygen is sharing its electron with hydrogen. And by sharing, I mean it's doing a half-assed job at sharing. It's not really sharing. It's trying to share, but it's not. But regardless, this is where we're going to be going into drawing these kinds of pictures where we can see the electrons and see what's going on in terms of bonding. And we'll learn about the different kinds of bonding. Some bonding electrons are given up or taken. Some bonding electrons are shared, right? And then some bonding actually has nothing necessarily to do with electrons directly. So we'll talk about all those different types. Okay, this is a little cheat sheet that might help you in the future if you want to take a picture of this or come back to this PowerPoint when you have a chance. It does kind of look like Minesweeper. It's like the same font too. But basically, this is showing you how many valence electrons each group has, right? So the first group here, they all only have 1 valence electron. The second group, they all have 2. Helium is a wild card over here. It has 2. Even though it's considered a noble gas, guess what? It only has 1 shell of electrons, and it has 2, it's full. That's why it's over here with the noble gases. Then we have 3, 4, 5, 6, 7, right? So we're going to find out, as you might be able to imagine, we want to get to 8. These metals here with 1 valence electron will react very well with the halogens that have 7 valence electrons, right? Those two are most likely to interact because guess what? 7 plus 1 is 8. Super easy. No craziness going on. Right, what gets harder is when you have things like, you could have 5 and 3 interacting, but then you could also have 5 bonding with a 2 and a 1, right? So that's why you can end up getting crazy molecules with 10 different things in them. But this is the basics. Now notice the metals and the weirdo anticide, I don't even remember what they're called, those things, the transition metals, they don't have valence electrons, right? They do have valence electrons, but they don't follow the rules. And they're very confusing, and they're something that you talk about in much more advanced chemistry classes. So when we talk about reactions and bonding, we might mention them, metals and kind of what metals do, but for the most part, metals are different than the way that the rest of these groups act. Thank you, lanthanide. Okay, I can read it, I just can't remember it. So metals are especially confusing because sometimes they share electrons among themselves and they create like a sheet of electrons on top of the metal, which is mind-blowing because nothing else can do that. So regardless, this will help you remember the valence electrons. I used to actually write this on top. Like I had a periodic table that I printed out with all the groups labeled, and then on top I would write 1, 2, skip the metals, 3, 4, 5, 6, 7, 8, and then I would just know helium was a 2. But that's going to help you when we talk about reactions. Okay, so that was the whole virtual session here. 40, oh, thank you, Elizabeth. Okay, so that was the whole session. I'm so proud. 48 minutes. I did super good at getting close to 45. There's not going to be an exit ticket for this, right? Because I did have you do stuff throughout the session. Obviously, yeah, that's my dog. He's like, I don't know what his problem is. He's been crying the entire time. Kendrick? But yeah, so please email me if you have questions. If you think you figured out the very special answer to why magnesium is usually a +2, just send me an email about that so that we can figure out if you get some bonus points for that. See, here's my dog right here. Whenever I do virtual sessions, he gets jealous. I think that's the issue. He wants me to talk to him and give him attention. All right, so otherwise, please shoot me an email if you have questions. Oh, I will say, as the last thing, make sure you're checking the modules in Canvas because there are lessons that don't have assignments, right? And they will still be tested. And a lot of them are really short. You could easily go through it in 10 minutes. So just make sure you're looking through those and you're aware of what's going on there. I did notice when I was doing grades for last semester that for physical science, people either had an A or a B, or they had an F. There wasn't a lot of in the middle, right? Which tells me that people were either trying or not. That's basically what this class is about, trying. So make sure you're trying, right? There's no reason that you can't get an A or B in the class if you're doing all the assignments and attending all the sessions. All right, so otherwise I'm gonna end this meeting. Elizabeth's gonna send me an email about the screenshot thing she did. And otherwise, I will see you guys on February 28th when we do a lab. Bye, everyone.